Take two.
What is the purpose of a drilling fluid? To clean the bottom of the hole, to cool, clean, and lubricate the drill bit, to maintain the walls of the hole, to transport cuttings to the surface, and to prevent entry of formation fluids into the wellbore.
Okay, folks, let's talk about drilling fluid. The diagram before you is the circulating system. Let's start by looking on the diagram at the center of the page at the very bottom where you see suction pit. The suction pit is a storage container for the drilling fluid. From the suction pit, the drilling mud will go through the suction line to the mud pump or mud pumps, where it is pumped to the discharge line and then up the standpipe, which goes up the derrick, through the rotary hose, through the swivel, through the Kelly, and through the drill pipe down through the drill collars, and it exits out of the drill bit through jets. It helps clean, cool, and lubricate the drill bit as the cuttings are carried with the drilling mud up the annulus and returned to the shell shaker, maybe a desander, desilter, mud cleaner, centrifuge, to clean the mud, to remove the cuttings from the mud before the mud goes into a settling pit to be reworked and reused. To ensure a quality drilling fluid, the mud engineer will use a variety of tools to measure the drilling fluid. The first one you see here is a mud balance. The mud balance measures the density of the drilling fluid in pounds per gallon. The next tool you see is a filter press. This is a tool that will measure the expected filtrate loss into the formation. The next slide you see actually is of a filter cake. This comes from the filter press. The filter cake represents the solids that build up on the wellbore to prevent more filtrate loss as we continue to drill the well. Ideally, this will form an impermeable barrier, preventing additional filtrate from migrating into the formation. The next tool you see is a VG meter, a viscometer. It measures the viscosity of the drilling fluid. It is important to have enough viscosity to be able to carry the cuttings to the surface, but again, if the viscosity were too high, it would create a whole new set of problems that we'll discuss later. The last diagram I think that you see right here is the well, and you see the drilling fluid is migrating down the drill pipe through the collars, through the drill bit, and comes up alongside the annulus. The whole idea behind drilling fluid is that there is pressure in the formation, as I indicated with the green arrows, that would like to come into our wellbore. However, if the drilling fluid has a high enough hydrostatic head to equal that of the formation pressure, it will keep the formation pressure in check, and there will be no flow of formation fluids into our well. Of course, there are problems if the hydrostatic pressure is too great, and that's for another video's discussion.
Let's look at a drilling fluid problem. To calculate the hydrostatic head of a column of fluid, we multiply 0.052, which is a constant. The constant was derived by measuring the hydrostatic head of a column of fluid 1 foot deep if the column of fluid weighed 1 pound per gallon. So we multiply 0.052 times true vertical depth in feet times the density of mud, the mud weight, in pounds per gallon.
So, if you were drilling into a formation with a pressure of 10,000 pounds per square inch at a depth of 16,000 feet, what should your drilling fluid weigh? Remember, the drilling fluid should weigh enough to create a hydrostatic head equal to the formation pressure. Okay, let's solve this problem. Step 1, we write the equation, 10,000 pounds per square inch, which is the formation pressure, and that would equal 0.052, the constant, times the true vertical depth of our well, which is 16,000 feet, times the mud weight in pounds per gallon. The missing variable is the mud weight in pounds per gallon. So we restructure our equation to read the formation pressure, which is 10,000 pounds per square inch, divide that by 0.052 times 16,000, depth of our well, and we get an answer of 12.0 pounds per gallon. In other words, 12.0 pounds per gallon multiplied by 0.052 times the depth of the well, 16,000 feet, would equal a formation pressure or a hydrostatic head, which equals the formation pressure of 10,000 psi.